Okay guys, so we are ready for the section 7-3 test review questions now. So again, these are worth 3 bonus points if turned in by Wednesday the 8th, which is the day of the test, the chapter 7 and 8 test. Okay, notice they also have to be completed correctly to get the bonus points. So number 1 says you construct 3 88% confidence intervals. A T interval with 9 degrees of freedom, a T interval with 4 degrees of freedom, and a T interval with sample size 30. So assuming the standard deviation is the same for all 3 intervals, write the 3 intervals A, B, and then C in order from the narrowest or the shortest to the widest or the longest. So let's see. When we look at our formula for our confidence intervals, it's always the point estimate plus or minus your critical value times your standard error. This part is your margin of error. Remember, margin of error formula? So what this is going to depend on, because remember your X bar, your sample mean, and your S, that's going to be the same for the sample regardless. Excuse me, or assuming those are the same for the sample regardless, we're just talking about what our degrees of freedom are. That's the only thing that's really changing between these intervals. So what changes then in our formula is the T star value, the critical value. So the sample with the largest critical value is going to have the widest interval because you're going to be adding the largest amount to your sample mean and subtracting it, I guess. The sample with the smallest critical value will then have the narrowest or the smallest interval. So we need to calculate what the critical values would be for each of these intervals. Okay, so it says 9 degrees of freedom, and we know that we have an 88% confidence interval or confidence level. So let's look. If it's an 88% confidence level, what's the area in 2 tails? 1 minus 0.88, maybe let's see, 0.12, right? So we check, is 0.12 one of our options for areas in 2 tails? No, unfortunately. 0.10 is an option for area in 2 tails. That would be with a 90% confidence interval, but 0.12 is not on our table A3. So instead of using table A3, we'll have to use the inverse T function. So we don't need to just know the area in 2 tails. We need to figure out that left tail area and be able to add it to that middle area of 0.88. So we're going to divide this by 2. That would be 0.06. Okay, so I'm going to sketch a quick picture here just to make sure you get the idea. Scoot that over, leave myself some room to write in what these critical values are here. Okay, so here is my T distribution. Okay, so let's say this is my middle area of 0.88. I subtracted that from 1 to find the total area outside of 0.88. So these 2 tails add up to 0.12. Since it's symmetric, half of it is 0.06. So this right here is the 0.06. Now, in order to find this T star value right here, the bound of all of this area to the left, I am going to find out what those 2 areas added together are. So what 0.88 plus 0.06 is, and I believe that's going to give us 0.94. So the area to the left of my T star value is 0.94. Now that's actually true for each of these, right? I'm using an 88% confidence interval in all of them, so the area to the left of the T star value will be 0.94. What changes is the degrees of freedom. So at first I do 9 degrees of freedom, then 4 degrees of freedom, and then it says a sample size of 30. So what would the degrees of freedom be here? Well, 30 minus 1, which would be 29. Okay, so let's type into that inverse T function. I'm gonna write the command just for the first one so that you can see what I'm doing just for A, and then I'll just use that for the rest. Okay, so remember inverse T is under distribution here. So I go second distribution, and then inverse T is the 4th one. So I can either scroll down to select it or I can choose 4. It asks me for the area and degrees of freedom. Remember, this is talking about the whole left area. So that's my 0.94. The degrees of freedom for A are 9. So I enter 9, paste. Okay, so again, what my command ends up being is inverse T, 0.94, comma 9. If I hit enter one more time, it gives me the value, which is 1.71. Let's round it to 3 decimal places, so 718. 1.718. Okay, so again, that's the T star value for A, 1.718. We could do the same thing for B. It has that same area, but now we're going to replace our degrees of freedom with 4. So again, I got a second distribution, choose the fourth one, inverse T. Area is the same, 0.94. Degrees of freedom now are just 4. Hit enter over paste and hit enter one more time to get 1.971 if I round to 3 decimal places. So T star is equal to 1.971. Then finally, I have to do this for C, where our degrees of freedom are 29. So instead of going through the process of second distribution to get the function, since I've already got it up here, I can use my up arrow to go ahead and select it, hit enter, and then just change that 4 to a 29, end my parentheses, hit enter, and I have, let's see, 1.602 if I round to 3 decimal places. T star equals 1.602. Just a quick refresher on how to find those T star values if you want to use the inverse T function, or if you have to when you have a weird confidence level that's not on your table A3. So let's use that information to see, we're going to write the 3 intervals in order from narrowest to widest. Again, the smallest critical value will give us the shortest interval. So we start with the smallest critical value, and it appears that is C. So C should come first. The next smallest is A, and then the biggest is B. So CAB is the order of nearest to widest intervals. And we can notice now that that depends on the sample size. So the larger the sample size, the smaller the interval, which means the more accurate your estimate will hopefully be. You have a smaller interval you're estimating with. Assuming, again, your confidence level stays the same. And then the smaller your sample size, or smaller your degrees of freedom are, remember this would be for a sample size of 5, that gives a degrees of freedom of 4, we would have the largest interval. So that's one of the reasons we like to have a larger sample size. It helps us make a more concise interval, a more accurate one. Okay, so let's move on to number 2. It says you are sampling from a population with a known standard deviation of 20. Okay, I'm already again thinking that's probably important. And want to construct a 95% confidence interval for the mean with a margin of error of no more than 4. What is the smallest sample size that will provide such an interval? Okay, so I'm going to look back over at my IS number 15 notes. I wrote in here that this is how we estimate, or how we try to find our sample size. And when we're trying to figure out a sample size to actually construct an interval. So we do n is equal to T star times S divided by E squared. And if we don't know what T star is, because remember, T star depends on the degrees of freedom, which depend on the sample size. And if we're estimating the sample size, we probably don't know the sample size, so we don't know the degrees of freedom. We use Z star in place of T star if the degrees of freedom are unknown. So let's see if we have all the information we need. We need to know the margin of error, E, and we need to know an estimate for the sample, or for the standard deviation. Usually we can use S and sigma, we can estimate with both. So it says there's a known standard deviation of 20. So that means sigma is equal to 20. We can replace that with S. We want to construct a 95% confidence interval. That's important. That's going to tell us what critical value to use. And it's for the mean with a margin of error of no more than 4. So at max, a margin of error of 4. So what is the smallest sample size that will produce such an interval? So remember, this 4 is really, it's not percentage points anymore. It's not a decimal like it was with proportions. Now it's 4 units, whatever our units are. So we can use 4 straight up. So let's figure it out. We are going to need n is equal to, we don't know the degrees of freedom we should use, so we're going to estimate T star with Z star times sigma, what we think sigma to be. Again, if you don't know sigma, like it tells us it's known, you can use S as the estimate and divide by E and then square all of that. Okay, so we better figure out what Z star value we need with a 95% confidence interval. So I'm gonna take a look one more time at my table A2 on the positive Z-score side. Let's see, for confidence level of 0.95, the critical value is 1.96. So that's what we fill in. 1.96 times S, which is 20, divided by E, which is 4, and then we square that. Okay, so I'm going to use parentheses here so I can square everything at once. 1.96 times 20 divided by 4, end parentheses, squared. 96.04. Okay. But remember, even though it's only 0.04 and it's really tempting to round down, we always round up with sample sizes. So the smallest sample size that will produce such an interval, I'm just copying this from the question, is 97. And it actually didn't tell me what they are gathering information about, so I'm just going to say 97. All right. Normally I would put units, but I can't here because I don't know them. So that is how we find a sample size. Okay, so let's look at number 3 then. It says below are the graphical representatives of 2 different samples from 2 different populations. So these are not corresponding to the same thing. These are totally different things. In each case, discuss whether the normal/large sample condition for constructing a one sample T interval has been satisfied. Now, I haven't used this word large sample that often, but it's referring to that is in greater than or equal to 30 part of the way we check the normal condition. So again, I'm going to flip back over to the IS number 15 notes, flip back one page. I was on the very last page, now I'm on the page before that. Here are how I check my normal conditions. That's one place you can find it. We also wrote this in our IS number 18. So either the population distribution is normal, N is greater than or equal to 30, and the CLT applies, or your sample distribution has no strong skew or outliers. So I'm going to check, since I don't know anything about the populations, whether they're normal or not, I'm going to check that N greater than or equal to 30. So this one says N is equal to 12. That is less than 30. The CLT does not apply. So I cannot use that way of satisfying the condition. However, in part B, N is equal to 45. Aha, that is greater than or equal to 30. So the CLT will apply. So I'm just going to go ahead and answer that question. N equal to 45 is greater than or equal to 30. So CLT applies. And I'm just going to put a check mark to indicate that the condition is met. Okay, so let's go back to A, because again, B, all I had to know was the sample size being greater than or equal to 30, done. I don't even have to look at this situation. However, if I did look closer than it, I would notice this is a box plot. And since this median line is really close to Q1, and that's really close to the minimum, it looks like most of the data is built up here on this left side. So this would be a right skew. The tail would be out to the right. It's pretty strongly skewed. If N was not greater than 30, then I would be worried about this. But since N is greater than 30, it does not matter what the sample distribution looks like. Okay, now looking at part A again, this N is less than 30, so it does matter what the sample distribution looks like. And I don't know about you, but that is a pretty strong skew, right? This is definitely right skewed. Definitely right skewed. So we are going to say that the sample distribution is strongly, that's not just a slight skew, that's strongly skewed to the right. Not only that, it appears it might have an outlier or two and has possible outliers. We are worried about that one. Since N equal to 12 is less than 30 as well, I'll say since n is equal to 12 is less than 30, CLT doesn't apply. So between those two things, n is less than 30 and there's the strong skew, the condition is not met. It's not met or it's not satisfied. So this is would be one of those times if, you know, this type of a sample distribution comes up in your checking of the conditions. If the condition is not met at the very end of completing the confidence interval or completing the test, you would say, I'm cautious of these results because the normal condition was not met. However, on your test, I'm probably going to give you one that is met, so you should check really closely to make sure it meets one of those three conditions. Okay, so now that we've kind of talked about some of the different ideas that come up with confidence intervals for means, let's go ahead and actually construct one. So flip our page over here. All right, it says about 217,000 high school students took the AP Statistics exam in 2017. The free response section of the exam consisted of 5 open-ended problems and an investigative task. Each free response question is scored on a 0 to 4 scale, with 4 being the best. So for one of the problems, a random sample, okay, all right, I'm thinking that's important. It's a random sample of 30 student papers yielded a mean score, so there's my sample mean, of x bar equal to 1.267 and a standard deviation of s equal to 1.230. Okay, so the first part says find and interpret the standard error of the mean. And interpret standard error. So let's remind ourselves, what is the standard error of the mean? We can look back at our formula sheet to see that. So under standard deviation, there it is, standard error of the mean is equal to s divided by the square root of n. So that's how we're going to calculate this. SE sub x bar is equal to s divided by the square root of n. I know both of those things. It says s is 1.230 divided by the square root of n is 30. Oops, square root of 30. Okay, let's plug that into our calculator, see what we get. We have 1.23 divided by the second square root of 30. It's 0.225 is probably fine. So a standard error of 0.225. So later when we sketch out our normal, I'm sorry, we won't be sketching out a normal curve for this one. If this were a hypothesis test that we were going to run, this would be the difference between the mean and each of these standard errors above and below the mean on a normal or t distribution, I should say. So it does ask us to interpret. This is not something that you will be asked to do on the test, but I just want you to see it to help you understand what this standard error represents. It also will help us understand what the t-value represents, because remember, the t-value is the number of standard errors away from the mean. So the interpretation of this is the sample mean score. That's our context. So sample mean score from a random sample of 30 student papers typically varies. Throwing it back to several chapters ago, typically varies from, or I guess say by at this point, but I'm going to say from the mean. And it's actually not just the mean, but the population mean, to be more specific. So the sample mean score from a random sample of 30 student papers typically varies from the population mean. Let's see, the population mean, I don't actually know, so I can't write that one in. Usually I would say of blank, but I don't know what it is. From the population mean by whatever that standard error is. So 0.225. I guess I could say points, but I don't know. This is kind of scaled, so I'm just going to say by 0.225. Okay, so that's the interpretation. Hopefully that, helps you remember the interpretation for a standard deviation. And that's why we use it to help represent how far away different scores are from the mean. Okay, so the next part, again, actually before I move on to the next part, I want to emphasize you will not be asked to do this on the test. You will be asked to do this, but not this. You may be asked to interpret a confidence interval, construct and interpret, but not the standard error. I just wanted to show you what the interpretation would be. Okay, so part B says construct and interpret a 99% confidence interval to estimate the true mean score on this question. So it's a 99% interval and I want the true mean score on this question. They're referring back to the question we were talking about up here, right? A free response question. Okay. Oh, for one of the problems, it says a random sample. That's what we're talking about. So that's the question we're talking about from the AP exam. So since it says construct a confidence interval, I need my 4-step process. So I'm going to look back over to my IS number 15 notes. I could look here to see some of the changes from sample proportion 4-step processes. But I'm going to look at the second to last page in part 2, where I actually have a 4-step process problem worked out to help guide me. So the first part is state. It says state the parameter you want to estimate and the confidence level. So notice those directions are the same for proportions and for means. It's just that our parameter now is a mean. All right, so we're going to state we want to estimate mu. That's our parameter now. It is the population mean. So mu equal to, and it's given to me in the problem, the true mean score on this question. True mean score on this. I could say question. I'm going to just really make it clear that we're talking about this AP test question. On this AP test question. Oh, with, and then we'll include our confidence level, with, let's see, what did it say? 99% confidence. Okay, so now we are ready for the next step. The plan step, we have to identify the appropriate inference method and check the conditions. So we need the name of our procedure, a 1-sample t-interval for mu, and we have to check the conditions. So let's label this step. Again, the name of our inference method is a 1-sample because we just have 1 sample. T, because we're using the t distribution for means. Interval, because this is an interval and not a test, for population mean mu. Okay, let's check those conditions. So the first condition is the random condition. And our problem way up here says we have a random sample of 30 student papers. Random sample of 30 student papers. Okay, that condition is met. The second condition is the 10% condition. So our sample size is 30. Is that less than 1/10 of the population size? So let's see, what is the population size here? We took a random sample of 30 student papers, and there were 217,000 total students who took this. So 217,000 total student papers. So 30 is definitely less than 1/10 of that, 217,000 student papers. That's my population. We're not often given the exact size of the population, but we were here, so we include it. That condition is met. Okay, the third condition is the normal condition. And this is for means, so I'm not checking large counts. Remember, large counts is for proportions. For means, I have 3 options. The population distribution is normal. In this case, it didn't tell me anything about the population distribution. N is greater than or equal to 30, and the central limit theorem applies. N is 30, so that works. If it hadn't, I would need to check the sample distribution. I literally can't do that here. I don't know what the sample values are, so I can't sketch them. It has to be that N is greater than or equal to 30, and it is. So N equals 30 is greater than or equal to 30. So CLT, central limit theorem, applies. Check. Okay, conditions are met. So next step is do. Let's see what we have to do. Remember, there are 4 parts to this: general formula, specific formula, plug in numbers, and write your answer. So our general formula for intervals is always the point estimate plus or minus the margin of error. So we start with that. Point estimate plus or minus the margin of error. And then we fill in our specific formula. The point estimate for means is x bar plus or minus the margin of error. That's our critical value. We have a t distribution here, so it's t star times the standard deviation or the standard error, which we talked about earlier is s divided by the square root of n. Okay, let's check that on our formula sheet. The specific formula for means is x bar plus or minus t star times s divided by the square root of n. We got it right. Okay, so let's see. I know x bar that was given to me in the problem. It's 1.267. I know s that again was given to me in the problem, 1.23, and I know n, that's 30. What I don't know yet is t star. So let me write down what that is going to be. So let's see, we have a 99% confidence level, and our degrees of freedom, that's the other thing we need to know, would be n minus 1. So 30 minus 1 is 29. So what does that give us for t star? Let's see if we can use table A3 this time. Again, 99% confidence level. So if our confidence level is 99%, 1 minus 0.99 is 0.01. That would be our area and two tails. So I need area and two tails of 0.01 and degrees of freedom 29. All right, area and two tails, 0.01. Scan that down to degrees of freedom of 29. There it is, 2.756. That is my t star value. 2.756. Okay, so I'm ready to plug all my values in. Again, x bar is 1.267. 1.267 plus or minus t star, which we just said was 2.756, times s, which is 1.230, divided by the square root of n, which is 30. Some of you have on accident been using 29 here. That's your degrees of freedom instead of your actual sample size. Be careful that you go back to n, not the degrees of freedom. Okay, so remember I'm going to type all that in at one time, use the minus sign first, and then do a second calculation with the plus sign. I don't want rounding error. I want to type this in all at once. So 1.267 minus 2.756 times 1.230 divided by second square root of 30. Hit enter. Okay, I get 0.648 if I round to 3 decimal places. Now, notice I typed in the 0 here for 1.23. I don't really need it, but it doesn't matter either way. Okay, I went up and selected that, and I'm going to scroll over to change my minus sign there after the 1.267 to a plus sign to get my upper bound. And I would get 1.88 if I round up to 6. Okay, so I'm going to go ahead and write this beneath. I get 0.648 for my lower bound for my calculator, and then 1.886 for my upper bound. Now, I'm sure some of you are thinking, oh gosh, can that be greater than 1? Well, if this was for a proportion, the answer would be no, but this is for a sample mean. The answer is yes. Remember that our sample mean should be halfway between this, and it appears that that is true. Okay, so let's finish up our final step. The conclude step for intervals is just to interpret the confidence interval. Interpret your interval in the context of the problem. So that's that sentence we put here at the bottom. We are blank % confident. So we are this time 99% confident that the interval from 0.648 to 1.886. Maybe we can put points as our units here. Remember, this is a score on an AP exam question. So I'm going to put points. Captures the true mean. This time it really is a mean. True mean, and I'm going back up to my parameter in context. So again, it's the true mean score on this AP test question. True mean score on this AP test question. Ooh, okay. That's not very high. Remember, the highest you can get is a 4. So apparently this question was rough. They did not do that well on that one, but that is our interpretation. Oops, I don't need quotation marks. Okay, so I am done with my confidence interval for a mean here.